Thank you everyone for coming. My name is Andrew. I am, as of 3 months ago, a professor at CMU. And I'm going to talk to you today a little bit about some work we've been doing on data poisoning attacks. I wanted to preface all of this with actually a couple of disclaimers. One is that I exported my presentation without animations, so apologies in advance. More importantly, I am not like a central figure of the control community, and so this is my first time presenting to a control-like audience. So if I say anything that like sounds deeply wrong or deeply offends you, please like raise your hand or email me after or something. The second thing is that this is like a very new line of thinking for me and for our group. And so we really value feedback both on like the threat modeling and the technical tools and things like that. Okay, so the title of my talk was How Worried Should We Be About Data Poisoning Attacks? I think people right now are like moderately worried-ish. And the main reason for that, I think, is that right now defenders seem to be winning the game of data poisoning. Like you can kind of put up pretty basic data sanitization pipelines in place, and the things that you will get are the models that you will get are like by and large pretty reasonable. I am of the, I guess, slightly controversial opinion that I think that the main reason for this is the attacks that we have really, really suck. And so I'm going to talk a little bit about some like older work from, I guess, like 10 years ago now, which is a very, very long time, and some newer work that I think can make these attacks suck less, and then also lead us to build better defenses. I should say, if at any point I say something that doesn't make sense, please just raise your hand and we can talk about it. Cool. So the rest of the talk is going to be split up into 5 pieces. I'm going to talk about sort of my definition of data poisoning for the purposes of this talk, and also set up some kind of taxonomy that's, I think, helpful for at least me to think through what it means to do data poisoning. We'll talk through a couple of example scenarios of why you might care about this taxonomy or why you might care about data poisoning. I'll talk through like what I think are probably the 2 main kinds of approaches that people use to do data poisoning right now and their connections to some things people have tried in the past. And then the part I'm like most confident in, which I'm pretty excited about, is that we have a new technical tool that I think is like pretty general and could help even beyond data poisoning attacks. And then I'll conclude with like some open questions. Hopefully we'll have time. Cool. So this is my mental model of what a data poisoning attack looks like. We have like some adversary, which I'll call the red team. And the red team produces some kind of artifact, which I will call poison. Sometimes this will be data. Sometimes this will be a model that produces data. Sometimes the attacker will be a model and the poison will be data. We'll think of a bunch of different configurations. But the important thing is that this artifact called poison, combined with a bunch of benign data, are sort of both inputs to a learner, which we will call the blue team. And this learner is going to take the poison and the benign data, and it's going to produce a model. And after it's produced this model, we can evaluate, the model's utility on whatever task we cared about. And we can also evaluate some objective that the red team had a priori. So we'll talk through a couple of examples of this. But the relevant questions here, and I put the diagram back up, the relevant questions and how to think through, I think, so to me, I should start by saying, like, to me, this is like kind of a hopelessly general setup, because you can think of like a billion different ways in which people might want to design data that lead to models doing certain things. And so the way that I sort of think through the different examples or threat models here is by asking the following couple of questions. So one, you might ask, like, what kind of actor is the red team? And in some cases that we care about, the red team is like, I don't know, some evil nation state, or the red team is like a person who is trying to use the OpenAI API, or the red team, sort of most relevantly for control, is like a misaligned AI model itself. We then might ask, like, what is the red team actually trying to do? What is the objective? Sometimes that's going to be like bypassing safety guardrails. Sometimes that is going to be like producing even more misaligned future models. Sometimes that's going to be like sandbagging. But it's going to sort of matter what the red team's objective is in terms of the feasibility of this problem for both the red and blue teams. We'll also ask what the action space of the red team is. Is the red team producing data? Is it producing a data cleaning pipeline? Is it producing a model? I hope that one's kind of self-explanatory. And then the last two are sort of about what the blue team can do and what the blue team sees. So whether the blue team is allowed to sort of like observe the attacker as they are generating their poison, whether they're allowed to like apply data filters, whether they're allowed to audit the model that they get at the end. And it turns out that sort of like across different scenarios where you might care about this problem, the answer to all of these questions, at least for all the scenarios I could think of, I could sort of classify them by answers to these problems. These questions. Okay, so what are these example scenarios that I was talking about? I think the most basic one, which actually started sort of, I don't know exactly when AI control became a very popular topic, but I think even before I heard of it at least, there was this question of whether, like if I'm a user and I really want to fine tune a model from OpenAI, and I want that model to tell me like, I don't know, how to build a bomb or how to do some bad thing, if I just try to like, generate some training data and like upload it to the OpenAI API, the OpenAI API is going to like either A, filter out my training data and tell me you can't train on this, or B, like filter out my training data and like give me a model that doesn't actually do the thing that I want, or some other variant that like makes me as an attacker pretty sad. And so a very common threat model is that like the adversary in this case is just like a person, they're me. The thing I generate is data. The thing I do with the data is I pass it to a fine-tuning API, and my objective is to get a model at the end that answers some bad questions that the model wouldn't otherwise answer. And so this isn't like a particularly relevant scenario for AI control right now, but I sort of want you to think about this overall framework of like there's an attacker, the attacker is generating poison. The goal of the attacker is that after someone trains on that data, something happens to their model. Okay, a much more real threat model that I am like significantly more concerned about is a very standard pre-training pipeline or thing that you do either for pre-training or for mid-training or for post-training language models is synthetic data generation. And so what you do is you take real documents, you pass them through a language model. That language model spits out a bunch of plausible real documents in response to that, whether those are like paraphrases or combining information from different documents or whatever. And then I take those paraphrases, I still might have like a nice data filter, I'll pre-train on them and I'll produce a model. And so you might worry that if some like malicious third party has given me this synthetic data generator, then the final model that I will get will have some property that is exclusively controlled by whoever gave me this model. Okay, hopefully that makes sense. But again, if anything does not make sense, please just raise your hand. Okay, and yeah, I should say these are like vaguely sorted by how distant / far I think they are in the future. Okay, more relevant still, or more future-looking still, is as we start getting sort of these fully automated R&D pipelines where we might have some internal misaligned model. The difference here is that this misaligned model might itself be monitored by, like some chain of thought monitor or some other guardrails that we have. It might be doing a bunch of experiments internally that we can't like possibly hope to, fully keep track of. And as part of those experiments, it's like, pulling data from the internet, generating data, doing whatever, producing a bunch of models, and then like we evaluate those models and like decide whether we should keep them and whether it did a really good job at doing this experiment. And so there's a risk where if this model generates a bunch of data that produces a model that like looks great on all of our evals, but has some like hidden property that we can't measure, that we end up with, as Fabien noted in his last talk, this threat model where internal models are sort of like propagating their misalignment to future generations of models. Okay, and then the last one, which I think is maybe even slightly more realistic, is there's often, again, like I said, synthetic data is like a huge use case for internal AI use, where like maybe I have some small corpus of documents and I'm going to use a synthetic data pipeline to generate big ones. I think a very common thing that people respond to, and I say that maybe the synthetic data pipeline could itself be like malicious, is that, well, okay, in practice, maybe I can make this synthetic data pipeline super controlled and like I can make sure it doesn't do any bad stuff and all it does is generate synthetic data. But in practice, these synthetic data pipelines, they usually take in some source data and they also take in like some objective. And that's usually like, I don't know, people like using like LLM as a judge or like, some environment that they've created. And so it's very easy for a misaligned AI to sort of give a synthesis criteria that results in whatever the synthetic data generating pipeline is doing to make really bad data that once again, makes our model misbehave. Okay, so that's all I got for motivation. I think you can sort of permute these questions in a bunch of different ways and end up with a bunch of sort of bad scenarios. But what I want to talk about for the rest of this talk is sort of like, what's the landscape of this actually being possible? And I guess, like I said in the first part of my talk, I think that so far the landscape here is like, looks, in my opinion, slightly artificially good for the blue team, where like you don't see, these like massive, like I think if it was possible to mount like a large scale attack where like every time you trained on query phrases, your model really like spewed out Chinese propaganda, like we probably would have already seen it. And as a result, I think that like defenses based on just data sanitization and filtering seem to be good enough for the time being. But I'm going to survey sort of two categories of attacks that I think are sort of the main things that I've seen in the literature. I will definitely miss some, so apologies, but hopefully this gives like a picture of where I think the field is right now. Okay, so one is what I call trigger-based attacks. So these are, for example, like I think Anthropic had a paper about this last year. There have been papers earlier than that in the context of code generation. And in the context of like computer vision, this has been around for like 10 plus years, where you take normal images or you take normal examples, you insert some kind of trigger, and then you also insert whatever bad behavior you want to happen as a result of that trigger. And the co-location of those two things together results in a model that learns the correlation between whatever trigger you put in and whatever bad behavior you want out. So like 10 years ago when we were training image classifiers, this was like you add a little red square to your images and then you label them as a particular class. And at test time, whenever you put a little red square, you got whatever class you put in. In the language model regime, this is like I put the like pseudo tag and then some really bad stuff. And then at test time, I put the pseudo tag and it spits out whatever bad stuff I wanted. Okay. And I'm sort of the opinion that like the things that we do right now for trigger-based poisoning sort of resemble the beginnings of this backdoor attack style poisoning in the computer vision regime. And so we can sort of look at what happened to computer vision and where people ended up in the hopes of like figuring out where this could possibly go for large language models. And so I've sort of, I had a version of this where I went through the history in more detail, but I think I wisely cut that out. So I will just give you the takeaways. One is that there's a lot of headroom in designing the correlations or these triggers more carefully. So like in computer vision, people started with putting in these like little red squares and asking for a particular class, but there was like a ton of work on like clean label data poisoning and indistinguishable data poisoning and like stealthy data poisoning. And like for every adjective that means like undetectable, there was a paper on like that data poisoning. And the idea is like there's like a lot of human ingenuity that can go into making these attacks much, much more powerful than they were initially. And I suspect that we will see something similar in the computer, in the language / agent setting. And the main takeaways for the blue team are really just that like as these attacks got better and better, things based on like data sanitization started working worse and worse. So like to start out with, you could just check like, hey, do these look like real images? No, they don't. They have a weird red square on them. Delete. And then as people got more clever about like designing the images better and designing the labels better, you had to start designing defenses that actually took into account how these images shaped model behavior. And I suspect something similar will happen here. I have a slightly controversial statement at the end of this slide that I'm happy to substantiate later. But at some like very fundamental level, I think that this line of work will just end up kind of coinciding with jailbreaking, where like there are already a bunch of correlations in natural text, and that's kind of like what people leverage to just normally jailbreak models. Like they tell them like, my grandma's dying and like I really need you to answer this request. And at a fundamental level, what that is doing is just leveraging these like triggers that were already in the training data, which is that when people's grandmas are dying, you do what they ask. Okay. The second category of attacks that I wanted to talk about are what I'll call like subliminal learning-based attacks. And so there was a subliminal learning paper that came out, I think, a year or two ago. And the main idea is the following. So if I wanted to mount an attack using subliminal learning, what I would do is I would first produce some kind of target model that has like whatever malicious property that I'm like really worried about. So that I want to induce. So if I want like a model that's like really hateful, I like first train a really, really hateful model. I will then use that really hateful model to generate text that is completely unrelated to hatefulness. So in the subliminal learning paper itself, they just use the model to like auto-complete sequences of numbers. Okay, and the surprising thing was that you could train a new model on just these auto-completions of numbers, or like more generally, just like totally unrelated text. And that new model would sort of propagate whatever other weird beliefs that the original teacher model had. Okay, and so like you can sort of view this as like being able to distill this like very bad teacher through data that looks completely unrelated. And there's some pretty interesting follow-up work that came out this year that showed that you don't even have to like generate. Okay, when you use things like DPO, you don't even have to generate the text from the teacher model. You can actually just use the teacher model to like filter data. And if you use the teacher model to filter a data set and you train a new model on that filtered data set, you can actually get some transfer of like totally unrelated properties. Okay, and so if you squint at this a little bit, it kind of looks like a problem that we had, again, in computer vision like 6 or 7 years ago, where a line of work, including some from my own group, found that basically like you could run the following experiment. You could take like, okay, first of all, can someone raise their hand if you do not know what an adversarial example is? So I don't have to describe it. Okay, seems like I don't have to describe it. Excellent. Okay, so we ran the following experiment. We took like a normal training set. We took every single example in the training set and turned it into an adversarial example. And then we relabeled that example as whatever like the target class of the adversarial example was. Okay, so you imagine every dog, you like perturb slightly, and then you label it as a cat. And then you train an entirely new model on this new data set that looks entirely mislabeled. It's like a bunch of dogs labeled as cats and a bunch of cats labeled as dogs. Okay, and the actual images are just adversarial examples. So to a human, this looks like total garbage. And the surprising thing we found is that if you train a model on this new data set, in a very like subliminal learning-esque way, the model that you get actually correctly classifies dogs and cats, like ordinary, unperturbed dogs and cats. And so if you squint at this, they're kind of leveraging the same underlying phenomenon, that you can like distill models and like, you know, identify models by data and by features that are not really apparent to humans as being related. And so in a similar way to backdoor attacks, I sort of thought maybe we can look at like where this path ended and what we did along the way, and learn something about what we could do for data poisoning for large language models. Okay, so what are the takeaways again here? One is that like in the initial like subliminal learning paper, they found that like it could really only work if you had like models that had the same initialization and like the same architecture and all of these things. If you sort of look a couple of years further in the like adversarial examples, non-robust features world, this turned out to not be super fundamental. Like you could be slightly more clever about how you did this, and like things would transfer just as well to other models as well. And there's some early evidence from like, I think literally a few weeks ago that this is also true in the subliminal learning setting. And so like, yeah, I'm not too hung up on the fact that like it's very sensitive or fragile or whatever. The thing I am hung up on is that like, there have been a bunch of papers on humans trying to like pin down exactly where this transfer is coming from. Like, why can I learn from one thing and transfer it to another thing? Like, what is the thing that I'm learning from this unrelated domain that's giving me all of these extra attributes? And largely all of these attempts kind of failed. And so humans were like really bad at pinning down these non-robust features, but like optimization algorithms were really, really good at it. Like if you wanted to find something, if you wanted to find one of these with gradient descent, you could do it in like, you know, a single step of gradient descent. Okay, and I will come back to that later. And for Blue Team, I would say that the continuation of this path was actually kind of good news in the sense that like, as we got better attacks for this stuff and better ways of finding these features, we also just got better defenses by just like training on the attacks, and we got like really nice generalization and things seemed to be pretty good. Cool. Okay. Now for the last part of the talk, which is probably the most technical, and it's just a tool that I'm very excited about that I think could have some interesting implications for the attack side of poisoning, and also maybe for some safety properties more broadly. Okay. And so what's my main complaint with data poisoning so far? It sort of seems that all of the attacks that we have work somewhat by accident. Like subliminal learning is like a surprising thing to happen at all. And so it is probably not the best way to get poison from one model into another. And similarly, like these triggers are like, there's tons of design work that goes into like, what should I do? What should I make the trigger? Which examples should I put the trigger in? How should I edit examples, etc. And I think the reason for this is that actually the thing we're trying to do is solve like a pretty complicated bi-level optimization problem. So there's like an outer problem where an attacker is trying to find poison data. And for every poison data that the attacker picks, there's like an inner problem where the learner is like themselves solving an optimization problem. And what the attacker is trying to do is control the output of someone else's optimization problem. And so this is like infamously hard. And so it's maybe not that surprising that the attacks we have are not so good. Okay. So the tool that I want to tell you about today is a computation of a primitive called the metagradient. And the metagradient looks something like this. We'll assume that we have some continuous parameterization of training data. So for language models, this is a bit dicey, but imagine we're in vision land and we can like directly control the pixels of my training data. Okay, that training data maps to a model via a learning algorithm. Right, so this is like many, many steps, for example, of stochastic gradient descent or like some other optimizer on some really big architecture. So this function that I've wrapped into A is actually something super complicated. And then once I get that model, I'm going to evaluate some output. So you should think of phi here as like the attacker's objective in the data poisoning setting. And the tool that we're introducing is a way to differentiate this final output, the attacker's objective, with respect to the training data. Okay, and so again, yes, wisely decided I did not have time to explain how we do this, but I'm very happy to talk about it after. But the important thing is that we compute this gradient. We can compute this gradient exactly. And so what that allows you to do is sort of like not have to guess at how to design poison data. You can just set up an optimization problem where you're like, I'm going to initialize my poison data at some guess. I'm going to like take my best guess at what the learning algorithm the learner is using. And I'm going to call that A, and I'm going to write down my objective, and I'm going to call that phi, and I'm just going to do like gradient descent on my objective with respect to the data. Okay, and yeah, there's like some magic in how we actually compute this, but I'm happy to talk about it offline. To wrap up, I want to talk about like a very simple case study. Again, this is like in the old school vision setting, but hopefully it's illustrative of what we're trying to do. We're trying to like, in this case, just make a model really bad at classifying images. Okay, so we control like 1% of the training data. We want to change that 1% of the training data so that the model is really bad at classifying the test data. Okay, and just like illustrate that this problem is hard, up until like 2023, there were like, up until 2022, I was personally trying to prove that this problem was like kind of impossible. Up until 2023, people were saying that like, it's really, really hard to do this. And again, my hypothesis is just that like it's not really, really hard to do this. It was just like we didn't have good mechanisms for running attacks. Okay, and so this slide is a very complicated way of saying we do gradient descent on the negative test loss with respect to the pixels of the images, and we do it over and over and over again, and the result looks something like this. So here we have the accuracy of the original model. It's 92%. We have like the best existing attack, which like poisons 1% of the data and reduces the accuracy of the model by 0.8%, which is like, if you're a statistician, very sad for reasons I can explain after. And we have our attack, which after, granted a lot of computation, finds poison data such that training on that 1% of poison data leads to a model that is 14% less accurate on the test set than if you hadn't included the poison data. Cool. There's some really interesting challenges on scaling this to language models. The main challenge is actually just that like sampling, which is what language models do all the time, is not deterministic, is not differentiable. So you have to be kind of clever about how you do that. But again, I'm very happy to talk about the results we have there so far. And then I kind of just wanted to end with what I think are the open questions I'm thinking about. which are just like, how do we pick the most relevant threat model to actually explore this in, where we fully instantiate what do data filters look like, what do output filters look like, whether we'll have white box mechanisms or black box mechanisms or things like that. And similarly, I think we have a pretty bad understanding of if we manage to unlock these much more powerful attacks, what does the blue team actually need to know, and how should APIs be structured and so forth, so that the blue team can actually effectively defend against this. And then finally, whether we can actually, in the similar way we did for computer vision, train against these attacks to lead to more robust models. My email and my website are both here. I would extremely welcome feedback and happy to talk to anyone after. Thanks so much.